Hello there, I am Davide and today I am presenting my Summer of High Performance Computing project, scaling the dissipative particle dynamics code DL-MISO on a large multi-GPU architecture. When it comes to process simulations, several methods are possible to perform a numerical experiment, but what eventually defines our result can be related to one parameter, the physical length scale that we are trying to characterize. We could be interested in looking at the interaction between molecules at a very small scale. Or we could prefer to simulate the behavior of a fluid on a larger scale to analyze its properties like velocity and pressure. In between the two, covering that range that is called the mesoscale, the dissipative particle dynamics method is the state of the art. Basically, a number of particles or bits is defined by a typical dimension that includes several small molecules or few more complex ones. Interactions between particles account for the thermodynamics of the experiment and form a system whose size is proportional to the total number of bits. In this way, the discrete nature of matter is maintained, but the physical scales that can be explored are wider than for the molecular dynamics. By extending the limits of the DL-MISO DPD code, we can run huge numerical experiments for increasing parallel execution and measure the code scaling. Our tools are the MPI library and the CUDA-C extension for GPU programming. When scaling, as we double the computational resources, we ideally expect a speedup of 2, which means that the current execution took half the time than the previous one. At first, we start running a serial experiment. Then we can introduce parallel execution of our code, so that the particles are splitted among the CPUs that are working together. Here, each color indicates a different process, and the particles continuously change color. The first scaling results are for a system of 3 million particles on CPU-only nodes. The code does not scale well, and this happens while we raise the number of MPI tasks, so that eventually there is no speedup at all. This scaling is due to the weight of communication on the total execution time. The more processes are executed, the more the communication will penalize the speedup. Let me now introduce the general-purpose graphic processing units. Originally used for 3D rendering, GPUs have been adopted as accelerators in several large supercomputers. While a CPU is composed of few cores with a lot of cache memory that can handle any kind of thread at high clock rate, a GPU has hundreds of cores that run at low clock rate and can execute only simple operations. Because of these features, GPUs present an inner parallelism that we will try to exploit. For example, we can try and render the real-time execution of a phase separation experiment. From the slow motion animation, we understand the potential of a GPU, which can repeat the experiment 5 times while the CPU terminates one execution. Finally, let's start our scaling experiment on the P-Stained supercomputer, the largest in Europe. This machine provides more than 5,000 hybrid CPU-GPU nodes. We ran scaling experiments for different system sizes, so to fully understand the possibilities of the GPUs for the DL-MISO code. The first result is for 3 million particles. The speedup is not so ideal, so this suggests that we can deploy far more particles. The next system counts 300 million particles, and the scaling is quite good, as we could run with 2000 GPUs. At last, we have performed the scaling for 3 billion particles. The experiment has shown good scaling on our GPUs, meaning that we are finally using properly their potential. This experiment will continue with a run on 4,000 GPU nodes. In conclusion, we have extended the capabilities of the DL-MISO DPD code, understanding that, thanks to a large usage of GPUs, it's possible to simulate wide systems. This result can positively affect the potential of such and similar codes. in order to benefit both research and industry.